Okay, the objective of today's lesson is to find out what happens when we have zero and negative exponents. In order to understand zero and negative exponents, we're going to pay attention to this chart that we have here. What we have is we have 2 to the, and for each case, the n is going to be up here, the exponents. So if we have 2 to the third, that's 8. If we have 2 squared, we get 4. 2 to the first, we get 2. If we stop paying attention to the exponent and pay attention to the chart, to get from 8 to 4, we end up dividing by 2. 4 to 2, we end up dividing by 2. So 2 going down, if we divide by 2, we get 1. So we see that 2 to the 0 power is 1. This is one of the proofs as why anything to the 0 power is 1. Now if we go down to the negatives, if we continue the chart of dividing by 2 every single time, we take 1 divided by 2 and we get 1/2. So 2 to the negative 1 ends up being 1/2. As we continue this pattern of dividing by 2, we get 1/4. Or in other words, 2 to the negative 2 is the same thing as 1/4, and then we get 1/8. We can continue and see this pattern with 3. 3 cubed is 27. Then 3 squared is 9. 3 to the first is 3. So this time we're dividing by 3, and 3 divided by 3 is 1. Or in other words, 3 to the 0 is 1. We continue to divide, we get 1/3, 1/9, and then 1/27. We can see the same pattern with 4. 4 to the third is 64. 4 squared is 16. 4 to the first is 4. And now we're dividing by 4 every single time. So 4 divided by 4 gets us 1. Or in other words, 4 to the 0 gets us 1. And then we continue this and we get 1/4, 1/16, and 1/64. So this chart helps us realize a few of the patterns that we're going to be taking a look at today. So what appears to be the value of a to the 0 for any number a? It is 1. Now there is one stipulation on this, and that is a cannot equal 0. To evaluate the expression in the form a to the negative n, what ends up happening is we end up taking the reciprocal. Anytime we have a negative exponent, it does not make the number positive or negative, but it just takes the reciprocal. So you get 1 over a to the n. One thing we can also see to understand why anything to the 0 power has to be 1 is by looking at a graph. If we take a look at the equation y equals 2 to the x, so it's a lot like our chart up here. Instead of n, we've got x. When x is 3, so we go all the way over to 3, we go up 8. Okay, when x is 2, 2 squared is 4, so we go up 4. When x is 1, our answer is 2. And then when x is 0, our answer is 1. And then it goes down to 1/2, and it gets really small. So small that it looks like it's going to approach 0 but never be 0. So that keeps going this way. The same thing is true if we had y equals 3 to the x. And y equals 3 to the x, when x is 3, we're way off the chart up at 27. When x is 2, we're even off the chart out here at 9. When x is 3, we're right here, but then it all comes together right here, and then it goes smaller faster. So even y equals x to the 3 goes through 1. We can do the same thing with y equals 4 to the x, and we'll just notice that it's going to go through here at 4, 1, and then 1, 0. So it gets steeper and steeper and steeper as that base gets bigger and bigger and bigger. Alright, so graphically we can see why it makes sense to have anything to the 0 power be 1. Alright, so definition of the 0 exponent. For a 0 exponent, we can say a non-zero number to the 0 power is 1. Now in this one statement, we really took care of two things. And just to re-emphasize, that a cannot equal 0. That's what we mean by a non-zero number to the 0 power. Otherwise, a to the 0 equals 1. All right, let's take a look at some examples here. 5 to the 0, since 0 sees the base of 5, the answer is 1. In example B, that 0 sees the whole base of -3, so the answer is 1. In example C, we've got x to the 0, but that 0, the base is only x, it's not 5. So we really have 5 times 1, which is 5. In example D, the base to the exponent 0 is just x, not the negative. So we have negative times whatever x to the 0 is, which is 1. And the same thing in example E. The 0 only sees the 9, it does not see the negative, so our answer is -1. Now to talk about negative exponents. In negative exponents, we say that a is a non-zero number. In other words, our base cannot be 0, and n is a positive integer. Then we have a to the negative n is the same thing as 1 over a to the n. If the negative exponent appears in the denominator, in other words, we have 1 over a to the negative n, then we take the reciprocal, and our answer is just a to the n. Let's take a look at some examples that was similar to that. In this example A, we have -1, the base is 4, that base will go down into the denominator. So it becomes 1/4 to the positive 1, but we don't have to write that. Okay, in this next example, that -4 exponent takes the base 3 down into the denominator, so we get 1 over 3 to the 4th, which we can evaluate 3 to the 4th as 81, so this is just 1 over 81. In example C, x to the -2, it just brings down our x to the denominator and makes the exponent positive. In example D, we pay attention to what that negative exponent sees, which the base is only x, so only the x is affected. 2 stays on in the numerator, and x to the 5th goes down to the denominator. In example E, we've got x to the -4. This -4 means that this base of x goes up into the numerator, and we have x to the 4th. The 1 becomes insignificant because the coefficient here automatically is 1, and we don't need to rewrite it. In example F, we apply kind of two properties. There's one property that says this exponent sees everything in the numerator and in the denominator, or we could just take the reciprocal of this because of the negative exponent, and then the 2 sees everything. We can take care of both all at once. That is, we can say that this 3 comes up to the top because of the -2, and then it's +2, and then 2 to the +2. So it takes the reciprocal, and the exponent sees everything. And we can go ahead and evaluate that, since we know that 3 squared is 9, and 2 squared is 4. So in cases where we only have one expression or one variable to the expression, these don't become too challenging. But here, we're going to see that A, we've got 3 to the -k. One second. All right, so in example A, we've got that k only sees the 3. So only the 3 is affected by the negative exponent. The 4 stays where it is, which is naturally in the numerator. So we have 4 over 3 to the k. In example B, we've got a negative exponent sees the g, and a negative exponent sees the h. But again, the 5 is not affected. So we have 5 over g to the 3rd, h to the 4th. In example C, there's two ways to look at this. One way is if you have the same base, you can add the exponents. And -3 plus 3 is 0. So 4 to the 0 is just 1. Another way to look at this is 4 to the -3, since it has a negative exponent, goes down into the denominator. So we have 4 to the 3rd in the denominator. This 4 to the 3rd in the numerator. which is 64 divided by 64. Again, that is 1. In example D, we could take care of the negative exponents, or since we have two negatives, we know we're going to have to raise a power to a power, which means we multiply. And negative 2 times negative 3 is 5 to the positive 6. In example E, we've got a negative exponent. It sees everything inside the parentheses because the base is everything inside. So everything goes down to the bottom. The parentheses have not gone away yet, but the negative 3 becomes a positive 3. Then we distribute that 3, and we get 1 over 64y to the third. In example F, the exponent negative 2n is the negative part. It brings this g up to the top, and it becomes g to the positive 2n exponent. We're not used to seeing variables in the exponent, but we can have variables in the exponent. That's fine. In example G, we have again the same situation as above, where if we take the two exponents and add them, we get 6 to the 0, and 6 to the 0 is 1. Example H is just like the one above, where we have a negative times a negative gives us a positive, so we get 4 to the 6th. This is a little bit about negative exponents and how they affect our expressions. In the next lesson, we're going to talk about dividing.